Hello, my name is Rich Marin, and I'm the CEO of Low Emissions Resources Corporation. You should all have received our teaser titled Introduction to a New Green Hydrogen Technology. It looks like this. That teaser explains why hydrogen technology is becoming such an important market for the world's future. It explains the problems with current hydrogen technologies, producing cost-effective hydrogen at scale and on a distributed basis without the carbon pollution that exists today. It then explains why green, sustainable, and cost-effective hydrogen production is critical to the world. This goes on to lay out the importance of hydrogen synthesis through green electrolysis and the place that we at LERC believe the latest proton-conducting ceramics, called PCC, play in the drive for technological efficiency and commercial scalability in this important arena, and why this PCC technology improves on the foundation the existing hydrogen electrolysis technologies offer, as shown in this chart. This video is narrated by our technology leadership team, a team that's been working together since LERC's inception in 2014. While 2014 is when LERC began working on ammonia synthesis using PCC, LERC shifted to hydrogen as a critical first stage of ammonia synthesis in 2019, as shown in this diagram. This video will explain the extensive scientific knowledge base that LERC has accumulated in the past 6 years of ammonia and hydrogen research. This is embodied in our world-class and unique team of scientists working at our state-of-the-art research and testing facility, strategically located in Dundee, Scotland, near our academic partner and a leading electrolysis research center, the University of St. Andrews. It is at this Dundee facility that our scientists have reached what they believe is a technical readiness level of TRL 7 in the composition and fabrication of high-tech proton-conducting ceramic cells. The story of material science and ceramic fabrication leadership continues from Dundee to our installation in Southborough, Massachusetts, where, in partnership with Upstart Power, an SOFC company, we have built our electrolysis reactor stacks that have advanced the product development through the technical readiness level 5 demonstration, which we will show you today on this video. We are moving steadily and convincingly towards a TRL 6 milestone later this year, and that will be the seminal evidence of the commercial scalability of this important technology. Please enjoy our video presentation.
Hello, my name is Jeff O'Leary, and I am the Executive Chairman of our UK subsidiary, LERG. We are a research and development company with a world-class team of scientists and a state-of-the-art facility creating electrolyzer reactor technology that will produce green hydrogen through the use of SOEC proton-conducting ceramics. We expanded our research space from our initial collaborative lab with Professor Irvine at the University of St. Andrews in January of 2019. Our new Dundee, Scotland facility is a fully equipped state-of-the-art lab, allowing our team to rapidly iterate the R&D process required to solve the demanding problems on the road to commercialization. Our team is focused on the performance of our PSOEC cell by selecting the proper ceramic cathode and coating materials and optimizing the environment in which they operate. The facility allows us to develop a repeatable fabrication process that has been captured by our Quality by Design program. Developing scalable, repeatable processes on an efficient, durable cell that can be transferred to partners like Kyocera, Upstart, and VHE is critical for our success. Our downstream partners have the experience to help us further refine our technology. This collaborative approach will lead to a cost-effective, reliable stack technology, giving our PSOEC hydrogen electrolyzer an important position in the growing hydrogen market. Let's take an inside look at our team and facility at work.
Located in Dundee, Scotland, our 7,000 square foot facility provides a completely vertical approach for the development of proton-conducting ceramic electrolysis. We have assembled the right team focused on hydrogen production in a community determined to be globally recognized as a center of excellence in sustainable mobility. Materials purchased from valued partners like Praxair Specialty Ceramics can be measured for particle size distribution to control packing density and the microstructure of the electrolyte and electrodes in the cell. This data is recorded by our quality design program during incoming inspection to ensure quality and repeatability. Material measurements also help control the porosity of the cathodes produced by LERG, further ensuring consistency throughout our process. Our team has the ability to challenge concepts through EIS modeling and test these assumptions on low-cost, high-throughput button cells. Our button cell process provides the foundation for our research. We can rapidly test new ceramic chemistries for conductivity and performance in various steam and temperature conditions. This leads to a more rapid, low-cost decision-making process than using full cell production and test. These initial material studies are transferred to our in-house production team. We have the capability to mix the powders on-site and process them in our semi-automated extrusion equipment. This allows for accurate, repeatable manufacturing of our proton-conducting ceramic cathode. The process is captured and transferred to Kyocera for further improvement and scale-up studies. Our in-house dilatometer and simultaneous thermal analyzer equipment provide rapid answers to complex questions. The SDA identifies thermal events in oxidizing or reducing atmospheres and measures the change in mass and heat flow from a sample as the furnace temperature changes. The proper sintering profiles, coefficient of thermal expansion, and composition analysis real-time has played a key role in our success. The dilatometer information enables LERG to manufacture durable tubular cells by matching thermal volume changes during sintering of the cathode, electrolyte, and anode. Our cathode functional layer, electrolyte, and anode coatings adhere to strict quality control processes, which ensure high levels of efficiency and durability during tests. Measuring properties like viscosity of the slurries is essential for the control of the extrusion and coating processes during cell manufacture. We rely heavily on our QBD system and the raw data when transitioning to high-volume manufacturing with our partners. On-site application of our coatings allow us to rapidly iterate combinations of various coating chemistries. This flexibility drives improvement because modifications to chemistries are driven by data collected by our team in real time. We also experiment with stroke and dwell times during the process to accurately control the desired thickness. Material selection and application techniques significantly affect the performance of the cell. This in-house capability makes the capture and transfer of information to production partners like Kyocera possible. We fabricate end cap and cathode collectors to improve leak rates and cell performance. Understanding cell leak rates real-time at predetermined process checkpoints drives process improvement decisions. In-house brazing shortens the time to test and allows for valuable research and braze materials applications. Our state-of-the-art single-cell test stands can emulate real-life reactor and stack conditions. These test stands allow us to change multiple parameters and optimize our operating conditions to increase cell durability and performance. Our stands can also simulate life tests on the materials that we use. We could then take the data off the single-cell test stand and use those same operating conditions and parameters on our stack tests. Once the cells complete their tests, we perform post-mortem analysis in our state-of-the-art analytical and optical lab. High magnification optical microscopes and our SEM provide large amounts of data on how our materials are responding to the environment in which they are operating. The SEM is an essential tool used to investigate materials for QC and to ensure cell layers are in specification. The SEM produces high magnification images of the ceramic surfaces, allowing LERG to determine the phase boundaries, porosity, grain size, thickness, and density of the layers in the cells. EDX processing gives precise elemental mapping of the surface. This function provides information on elemental distribution and diffusion throughout the ceramic materials. 3D mapping gives height, area, volume, and ISO compliant surface roughness information. The ability for our highly skilled scientists to vertically integrate our R&D process in one location allows for an extremely high level of collaboration and rapid iteration of technology improvements. We feel we have the premier proton conducting ceramics research facility in the world and are ready to conquer the challenges on our journey to success.
Hello, my name is John Hughes, and I'm the Vice President of Engineering at Low Emissions Resources Corporation. I'm here today to talk to you about the productization and commercialization of LERC's groundbreaking hydrogen electrolysis technology. Having proven the technology at the single cell level, the next step towards TRL5, and ultimately to full productization, is the bundling of multiple cells together to create a reactor stack that produces larger and more meaningful amounts of hydrogen without introducing significant new energy losses in the connections between cells. To achieve this goal, LERC has partnered with Upstart Power, located in Southborough, Massachusetts. Upstart Power was formed in 2017 from a management buyout of the hydrocarbon-fueled solid oxide fuel cell business from Ballard Power Systems. Upstart Power is focused on the commercialization of SOFCs for industrial and residential applications.
As this presentation has shown, our team in Dundee has made substantial progress with proton conducting cell technology over the last 12 months. We've accumulated sufficient test data on individual cell performance and the optimization of operating conditions to achieve TRL7 at the cell level, and we're currently pushing our single cell tests to 1,000 hours. Prior to the addition of catalysts, our cells showed energy consumption of about 45 kilowatt hours per kilogram of hydrogen. Initial cell tests with catalysts show improved performance in both energy and degradation metrics. Achieving TRL7 classification at the cell level has proven sufficient reliability to now focus our efforts on stack and reactor development. This multi-cell stack configuration includes several design improvements from single-cell tests, including cathode current collectors, improved cap designs, and cell interconnects. We are currently running multi-cell stack tests at Upstart in Massachusetts. Successful multi-cell stack tests will demonstrate a TRL5 level status. The stack design we are now testing is the first step in proving the scalability of our proton conducting cell. Partnering with Upstart in stack design allows us to expedite the foundational research and design modifications that can be transferred to our scale-up partners. As we look to the future, our cell research in Dundee indicates that there are still many technology parameters we can modify to improve our cell performance. Our coatings can be enhanced with recent new material discoveries. Kyocera is developing a process to produce a thinner electrolyte coating, which will reduce overall resistance. Improving cell ovality will improve system seal integrity and reduce system degradation. Additional testing will also allow us to further optimize the operating conditions and maximize the overall performance of the technology. Increasing the repeatability of the cells and improving the efficiency of the stack design will lead to larger multi-stack configurations and a future TRL6 designation. We have carefully selected strategic partners like Upstart, Praxair, VHE, and Kyocera. These companies have many years of experience in SOFC and SOEC cell manufacturing, stack design, and plant design and construction. Each partner company has already developed a strong working relationship with our R&D team in Dundee. With our groundbreaking technology and the relationships we have with these industry leaders, we believe that we have all the pieces in place to develop the optimal solution to meet the increasing demand for green hydrogen production.
I trust you enjoyed that presentation. In closing, we have tried to show our vision to you of the hydrogen-based future. We've also shown you the high quality of the LER research and development efforts. You've met the leadership team and you've seen the work underway. The value proposition of LERC lays out as its accumulated knowledge and IP base, its fabrication process and the IP attached to that, and the PCC SOEC cell and stack performance levels, which are commercially noteworthy. The one-of-a-kind high-tech ceramics research lab and testing facility in Dundee, combined with the development partnerships with Upstart Power, Kyocera, and VHE Engineering, have come together to make great strides in moving green hydrogen synthesis into its logical next generation of efficiency. As we aggressively move into the next stage of commercial product development and scaling, we are looking for more partners to join us in this exciting journey. Please contact us for more details on the scientific data progress and the investment opportunities available, the need for efficient green hydrogen synthesis, and the role of high-tech ceramics make this an important moment in technological advancement. Thank you very much. As a pleasant postscript to this video, I would like to add our thanks to Scottish Enterprises for hosting the video, and also to especially thank them for very recently approving at the highest levels a significant grant to LERG for its work in hydrogen synthesis. Thank you for joining us, and thank you, Scottish Enterprises.